So hello, everyone, and welcome back to Programming Quantum Computers. We're on chapter 8 this time, which is quantum phase estimation. So I've been taking the approach of don't try to figure out what this is for, just try to figure out what it is, because starting in chapter 9, we're going to actually look at applications. So I'm kind of trusting that this will make sense at some point, and it definitely builds on what we've seen so far. In fact, it uses the inverse QFT that we saw last time. So it should be a lot of fun. Okay, I'm gonna share my screen, and then I'm gonna kind of take the Lin approach this week. I'm not going to kind of go all the way through the chapter, paragraph by paragraph, but just to kind of take a look at some of the things that I found interesting. And then I have some experiments, I will say, that I did to help me understand this a little bit more. So the thing about eigenstates and eigenphases, which is the first words that they throw at us, is, what is that? The general idea is that QPU operation, and I don't know if this applies to everything, it's kind of implied that it applies to a lot of operations, actually has this state known as an eigenstate, where if you apply the operation, you get exactly the same output. And so I find that kind of interesting because it's like, well, it's almost like a balancing point. You know, it's like, okay, well, if I try to measure it, or if I try to change it at this point, it's just going to stay where it is. So it's almost like it's finely balanced. And rather than look at these pictures, I'm going to go to code already. So I have some experiments set up, and in the Slack, I have these on my quantum programming experiments GitHub project that I have. And so these are all there if you want to look at them later. I need to talk to Nuri and see if there's a way to get them into this little dropdown, because that would be cool. I was thinking about that today. Okay, so before looking at eigenstates, let's just kind of look at what we normally have with a had operation. So here I have a 1 qubit register that's initialized to 0. So on line 4, we write a 0. And then we had it down on line 11. And this is what we're used to seeing. So before the had, it's in a particular state, in this case, 100% 0. And then when we apply the had, it puts it into a superposition. And in this case, it's kind of a 50-50. It'll be a 0 or a 1. Excuse me. And then if we start out with a 1, then we get a different behavior. So in this case, we start out with writing a 1 to our register. And then when we had it, we still end up with that 50-50 state as far as the amplitude is concerned. But the relative phase is 180 degrees. So it actually changes the relative phase. And so this is what we're used to seeing. Now, what's interesting about these eigenstates is, in this case, if we take a 0 and then we do this rote y 45, we end up with a state where a had doesn't change it. So here I have my cursor before the had, and we can see that it's the numbers from the book. I think this is like 84 point something percent or 86, and this is like 14 point something percent. And then after we apply the had, there's no change in our circle diagram. So the had has no effect. And so this is known as an eigenstate for had, where you apply it and it doesn't change anything. Now there's also something that goes along with this, which is an Eigen Phase. And this I have in the next example, where we have a different starting state. So in this case, I'm still writing a 0. So I'm starting with a 0, but instead of doing the rote y 45, it's a rot y negative 135. So if we look at the state that we have after initializing, the percentages are the same. So we still have this 14%, 85 point something percent, but the phases are opposite. So the relative phase is 180 degrees. Now, the interesting thing here is when we apply the had, the percentages stay the same. So the amplitude is still the same. The relative phase is also still the same, but the global phase has changed. Okay, it took me a while to grasp that. So if I go back before the had, you'll notice that the 0 is pointing up and the 1 is pointing down. And then after the had, now the 0 is pointing down and the 1 is pointing up. Now, relative to each other, there's still 180 degrees difference. So the relative phase is unchanged. But the global phase is different because they basically both rotated the same amount, if that makes sense. So what do you think about that? No comment? Okay. Again, how is this useful is the question. Well, what's interesting, so we have the eigenstates, and this degree of rotation of the global phase is known as the Eigen Phase. So on our first example where the global phase remains unchanged, this has an Eigen Phase of 0 degrees. So it doesn't move at all. For the second one, where we have our global phase rotate, this has an Eigen Phase of 180 degrees. So again, the question is, why are these useful? I don't know yet, but what I think is interesting is the promise, because what we're promised in the book is that we can calculate these eigenphases for a particular operation. But what that also means is that we can get, let's see if I see this right. We can get data from a register that's in superposition without reading it. So we don't alter that, but we have something that we can read. And so this calculation, being able to get data out of superposition seems to be really important, because it seems like the last few operations have been all about, okay, how do we get data out of something that's in superposition? And so in this case, I see the same thing where we have an input register. We can get data into an output register that pulls from the input register, but we don't actually change the input register. And then we can read that safely without impacting the input register. Let's see if there was. Oh, and then I do not have this, but there was a note here for anyone with linear algebra experience, which is not me. Eigenstates and eigenphases are eigenvectors and complex eigenphases of the unitary matrices regression QPU operation in the full mathematics of quantum computing. That means absolutely nothing to me, and I'm okay with that. Lynn, you've studied linear algebra. Does that mean anything to you?
I had to look it up because
Okay.
I don't use it every day. Basically, you're doing computation on real and imaginary numbers would be the way that I would summarize it.
Mm-hmm.
And
Okay.
the imaginary portion is being represented in the eigen stuff. And so the application is it allows for complex computation because you have real and imaginary in the register, so your intuition is correct. Mm-hmm. And again, even not knowing the specifics of it, understanding that you can do complex computation with multiple primitives, you could see where that might have promise on complex computational problems. It's really tricky without the math, to get what it's doing. And so
Mhm.
your go on faith is admirable.
I'm perfectly okay without understanding the nitty gritty details as long as I get enough so that it ends up being useful to me.
Mhm.
And so I have hope that this will be useful once we get into the programming bits. And then we actually did see some complex numbers when we were talking about QFTs and looking at the waves.
Mhm.
Again, we ended up, for the complex ones, we ended up with the mirror image when we were
Mhm.
looking at the QFTs, if I remember correctly. So yeah, it's interesting. So then it talks a little bit about how this phase estimation is calculated, and it is estimation, like a lot of things in the QPU world. And we'll actually see how much of an estimation it is in the second example they have. In the first one, it's a little more definite. And then it's kind of interesting talking about the calculation that you need to come up with to calculate the phase estimation, which is coming up with a conditional on the operation that you're using in a way that it will fit together. And rather than looking at this code, I'm going to go back to the sample. But before I do that, I just want to skip to this nasty calculation here, because what happens when we run this phase estimation is we end up with a register, which is a number of qubits. And so there's the example here where we have a value of 8 in a 4-qubit register. But that is not an angle, that's a number. And so there's this fun calculation to figure out how do we get from that number to an actual angle. And this kind of goes back, we'll look, where was that? Did I miss that diagram? Oh, actually, this diagram kind of shows it. Where, and this is actually something we saw with the QFTs, where we're looking at the number of rotations that we get when we're going around. And so we can use this calculation to get an angle out, which kind of coincides with that number of rotations if we were looking at QFTs. The bad thing about this particular formula is that it's not the value that we want, because we actually want this theta. This is the value we're solving for. So let's see. I had to pull out my old school algebra and I'll hold it up to my camera. Solve for theta, theta of j. Because what I wanted to do was I wanted to output the actual angle. And so now let's go and look at that code. And for this example, this is from the 8-1 example, but I'm not using the one in the book. I'm using the awesome one that Lynn did instead. And the reason is, let me just open up that one real quick just to show why this one is more interesting for me to read. Is in the original, there's a lot of variables with comments on them. So this one says, this is the size of the output register. This is the size of the input register. This is what this is doing. This is what that's doing. And Lynn said, let's forget about all that. And so we're going to have a variable instead called input register size eigenstate.
So yeah, so one of the techniques that I use generally is if I'm trying to understand some code, I will refactor to rename variables and methods to remove all the comments because it reduces the cognitive load. And particularly this was inconsistent. Like sometimes it would have comments,
Mhm.
sometimes it wouldn't. The comments were also not always on top, sometimes on the side, even to the point of like method names. There's a conditional had, and then there's another had, and one was like Hadamard, one was C had. And even also the brackets, like the brackets weren't lined up because like I'll
Mhm.
collapse the functions to
Oh, yeah.
understand. And I couldn't. So there was a lot of like little code reading aspects that I did that I'm going to do for the rest of the code in the book, because it's the way that I process code. It's my way of reading it. And so I was happy to see that Jeremy found it to be helpful as well. And I posted it on my GitHub.
Yes, yeah, and I definitely appreciate that. One of the things for the week that I missed, one of the things I didn't like is they showed two different ways of doing the inverse QFT. And that bothered me, not because I need to understand there's different ways of doing inverse QFT, but these are concepts that are kind of big and outside of my scope. And so the more cognitive load you add to it, the less likely I am to grasp it. And same thing here. So like here, this is the conditional had, and the book does have C Hadamard as the full method name. And then just for the regular had, you can use had or Hadamard, which is nice, but again, consistency is good. I actually like this just because it says Chad. So I'm using, we're using the Chad function. So we gave him a nice name. Okay, so let's go back to our phase estimation. So the setup that we have at the beginning is the same setup that we have in this one, where we have an eigenstate, or yes, we actually have a state which is an eigenstate of had, where we have a 180-degree relative phase. And then again, if we apply the had, we have a 180-degree global phase. And that's actually the number we're trying to get from this phase estimation operation. There's a lot of terminology.
And before you go through that, from what I understood is the reason why we're trying to estimate phase, or one of them, is because every single Q operation has its own unique phase that its eigenstates are in, right? Or something. I thought that was interesting. And so it kind of seemed like they were implying if we have a way to measure what the phase is, we can somehow tell what operation we've used or somehow applies to whatever we're doing. Again, I'm not sure why we would do that, but that was something I was hanging on. Like, why are we estimating the phases? Oh, because there is only one operation that would actually align with this phase. So that, I don't know. Again, that's something that was unique and interesting to me that I'm filing away for hopeful for you. So knowing that, then it's like, okay, let's figure out how do we estimate this thing.
Yeah, and it the book, I was looking through it again, and let's see, it actually did say something to the effect of, if we already know this, then why are we setting up this thing so that we know it? And I don't remember where that is. I'm not going to try to find it now, because that would be a waste of our group time. And again, I'm kind of taking it on faith that because this is something that we can do on qubits in superposition without modifying that position, then I'm assuming that it's useful at some point once we learn more about how this actually applies in real applications. So yeah, I'm definitely going on faith at this point.
And the other thing too neat is that diagram where it almost shows like we're building a little circuit where you have inputs, you have some control, then you have outputs. We're again, yeah, that whole thing. And it just hit me right now. It's like, we're again learning how to get data out of our input without changing the input. And where is the answer going? It's going into these other qubits that you have. And in earlier chapters, we had scratch bits. And so it's helping me understand more and more why we need these large multi-qubit systems, because even though your inputs and in your various circuits may not have a whole lot of qubits required, to do these crazy operations, you have to have this storage area. You have to have this area where you're putting this knowledge, because you can't change your inputs without affecting.
Yeah, and I wish there was a way to have the visualizer do this.
Yeah.
Because this makes it very clear. Here's our input register, here's our output register. And from looking at this, I can tell they're unchanged. And then here's the output register, or I'm sorry, the input register when we're done. Here's the output register at the beginning, and here's the output register at the end, and we can see how that's different. But unfortunately, the visualizer mushes them all together into a single set of circles. So to say, okay, well, I'm going to extract this one is a little complicated. So, so this initial state is the same that we had, looking at, okay, we know that this has an eigenstate with an eigenphase of 180 degrees. And then it runs the phase estimation, which is this whole thing here. And then we can get a value out of that. The phase estimation, I didn't try too hard to understand the details of this, because it does talk about how we need this conditional unitary function in order to do it. And then the conditional unitary function, this is specifically for the had operation. And so the idea is, since had has a corresponding conditional had operation, this function is pretty simple, if relatively speaking. It's short. I don't know if simple is the right word, but it's short. If we had something that did not specifically have a conditional version of itself, then I can imagine that this would get more complicated, because you'd have to expand it into multiple operations. So looking at this, so this phase estimation does take an input register, an output register, and then the function. And then I didn't try to go too far into exactly what this is doing, but it seems, and maybe actually you can put your input to help clear it up a little bit, because initially we do a had on the output register, which is this right here. So all 4 of our qubits. And then there's a for loop that then runs the conditional unitary. Now, this is where I'm a little bit lost on the code, because it's looping through based on the output register number of bits, which is 4. So there's 4 qubits in our output register. And so that's what this for loop is doing. So in my brain, it should run this line 4 times. But because of this if, it looks like it's only running 1 time. Is that because this is the operation right here where we're doing a conditional had? Does that seem like I'm following what this is doing?
Well, the other way to look at it is to look at line 22, which is in the inverse Q of T.
Right, which starts right here, and everything past that is inverse Q of T.
Right, so then that's the way I understood it. So yes.
So I'm not sure why the conditional here is having it only run for the first.
Yeah, I couldn't really get that either. I mean, the method name being called unitary, and was like, okay, single. And to tell you, in subsequent chapters, your intuition is correct. When you have more complex functionality, then you actually have to decompose your complex methods into unitaries. But I don't exactly know why. I can see what, but I don't know why. So again, I was kind of like, I was like, okay, that's what it does. I'm not really sure why it has to do it that way, but that's what it does.
Yeah, and that's where I am, and I'm okay being there.
Yeah,
but
me
if
too.
someone had some some insight. I'm always open to more insight.
Well, one of the things I'm trying to do with the subsequent chapter code is on like little methods like that. Because again, other things that I did here is I reversed the order of the registers because originally it was output over input, which seemed weird to me. And then the helper methods were not in order, because the way I read code is like the top method and then it calls the helper methods, and that should be below, right? So I can understand.
Yeah.
So one of the things that I would do if I had more time, and I'm trying to in subsequent chapters, is to, it's called inline, I think, get rid of some of the helper methods, because I don't think that the conditional unitary method helps us understand what it does. So I think, like you said, we're looking at that if line 27, 28, and we're saying, okay, we can read the code, but we really do not understand why that code has to do that. So one of the things I try to do is remove anything excess. So I would, and I'm working on that for chapter 12 actually right now. I'm trying to decompose to make methods that are more readable, that you don't have to, again, reduce the cognitive load, because I can't follow the why here. So
yeah, and in this case, this phase estimation, I mean, again, this would work for a variety of different functions. This just happens to be the one we're working with right now.
Right. So yeah.
And now that you were saying, so when you're talking about reversing the input and output registers, when I initially saw this, I was actually thinking the same thing. It kind of is easier for the input register visually to say the input and output. But just now, as I was thinking about this, it might the circle diagram might actually be easier to read if it is the other way, because then the input register would be on the high side.
Interesting. Never thought of that.
And so then everything. So basically, I think you could ignore everything like in the second half of the circles. I don't know if that's quite right, but does that make sense?
Yeah, that's an interesting insight.
Yeah. Okay, so that's something to play with, is flip them around and see what the circles do. I've kind of been ignoring the circles because there's so many of them. They have to be really little. So
yeah, when I was also wondering why we were only going through it once. Like you said, you looped through it 4 times. In that, on line 21, it has that 1 with a left shift. I had to look that up.
Yeah.
With the J, and so really you end up with a whole bunch of zeros and a 1 at the end. And every time you shift it, it adds zeros to the right-hand side of that 1. The very first time you run through it, the 1's at the far right side on the lowest bit, and every subsequent time that 1 moves up. Well, if you look at line 27,
yeah,
you're ANDing it with 1. So you're basically saying, whatever my control is, if there's a 1 at the very end, then go ahead and do this. Well, I wanted to inline this stuff too, because like you're saying, Lynn, as it's jumping around, I'm like, why is this doing this? Let me just inline it. And if you realize that, oh, the very first time when j equals 0 is the only time you'll have a 1 at the right end, that is the only time it's going to run. Well, then forget line 20, 21, forget the whole function. Just put my Q target in there. But then I realized, oh, we're using a very simplistic pad. So as we get to more complex operations later, maybe we are going to call this phase estimation with some sort of more complex conditional.
We are.
Yeah. To where it'll run it more often. It won't run it only when j is equal to 0. So
the other thing that I tried, I'm sorry.
I was just going to say, I think they've given us a fairly, like a utility function. And in this one example, the function's so simplistic. It's like, well, why have the utility function at all? When and later on, it's like, no, you're going to be using this utility function several times in different operations. You'll need those extra loops and stuff, though.
And actually, I didn't try this, but I'm going to try it now. Because why not experiment? Because in the book, it implies that there's a built-in phase est function. Is that okay? Apparently that's not what it's called.
Let's go see what it is.
But I thought it said there was a built-in phase est. Okay, so put this back. That's why I always practice live coding. Okay, what did I?
Okay.
Estimation.
Oh, it's a QC dot phase est.
Oh, is it Q? Okay,
Thank you, Rick.
QC.
Although,
Okay,
oh, yeah.
well, let's try. Let's copy this line. QC dot. Okay, that would make sense because it needs to come from somewhere. Phase est. No.
Well, it doesn't give you the circuit diagram, but it gives you the right answer at the end. Oh,
No, there it's an error. It says QC phase
Not-
est is not a function. So okay, well, something to look into. Won't worry about that right now. One thing I did try was I kind of said, okay, well, what if we have two input registers? What would happen? And this would now no longer be an eigenstate for had, I believe, if we had two input registers. So I was just curious. It still ended up with a single operation, a conditional with two hads. But anyway, that's just something I tried just to see what would happen. Okay, but we definitely have kind of three steps. We have our had of the entire output register. Then we have our conditional unitary, whatever it does. And then we have our inverse QFT, which is the rest of this function. And then what I did was I added a new function, which I called print output angle. And it took that, the one we saw in the book, and flips it around so that it gives us the theta. So this angle, which out here says 180 degrees, is the actual phase. And there's a little thing here. It doesn't like my 2 stars, which is how you do a power 2 in JavaScript. So, but it works. So the little yellow triangle makes me nervous, but it works. So this does give us our phase estimation of 180 degrees. And then if we were to use our 45-degree one, which again is one where our phase does not rotate, then this tells us that the Eigen phase is 0. So it's giving us the same thing that we saw, I'll say intuitively, when we were looking at these separate diagrams. So yeah, it's always interesting to just kind of stick in different values and see what happens. So this is how phase estimation works. Now, in this case, 180 degrees kind of divides nicely into an even number of qubits. So we can actually change the output register to 3 qubits and we'll still get an accurate answer. And in fact, because I like to experiment, I changed the output register to 2 qubits and still got the answer that we expect. So this is enough resolution to get to what we want. I didn't try 1, but does 1 even work? Let's try it. Apparently 1 qubit is enough to get an accurate estimation in this case. And the reason why this is important is because the next example shows one where it's not so even. So it actually is an estimation. And let me just rerun this. So again, this is the Lin refactored version. And this, what it does is it basically ignores the input state. So even though we're setting the -135 on our input, that gets ignored because this is the conditional unitary is set up so that it always spits out 150 degrees. So there's no, I don't think there's any QPU magic in this case. I think it's just doing things to make sure you always get 150. It's not from what I understand, it's not related to a specific eigenstate of a real QPU operation. Is that what you got as well?
Yeah.
And so in this case, it shows how this estimate really is an estimate, because in this case, having 3 qubits, which is what it starts at, that's not a high enough resolution to get an even 150 degrees. Because let's see, if I think there's a picture of this when we're looking at the rotating circles. Maybe not. But again, kind of thinking about the rotating circles that we saw with the QFT and inverse QFT and all of that, basically 150 degrees doesn't divide evenly based on the number of qubits that we have. So it really can't tell, okay, exactly how many rotations is this doing? So it can't give us a precise angle. So instead we get an estimate. And because it's an estimate, because the resolution isn't good enough, it's also not 100% determinate. So I believe the book says, in this case, you'll get a close answer about 40% of the time. So if keep your eye down here on the 135 at the bottom, I'm going to run this a couple times. So there I got a 90. There's a 225. There's a 135, a 180, a 90. So, and I'm clicking it multiple times, and 135 is coming up more than any other number, but it's still not 100%. So 135 is kind of the closest that we can get with this resolution. And so it's not exactly on. So I tried different precisions. So let's try a 5 to see what happens. Okay. Shrink this. So now I have 146.25, which is a lot closer to 150. And it's still not going to stay at that number. It's still going to kind of jump around to a lot of numbers. But 146.25 and 157.5 seem to come up a large majority of the time. So that means we're kind of getting closer, but we'll still see outliers that are kind of far at either end. And then I think I tried 9, and I'm not exactly sure what the limit is, but the more you add, the much larger the circuit gets because of those loops. And so now this is showing, 149.7 and 151.1. So it's, again, kind of getting close to that 150. I don't actually know if there's a number that 150 will divide into for this or not.
36 or something. What I didn't understand is the picture diagram he has in the book for figure 8.5 does not match the output, no matter how many times.
Figure 8.5.
Back up page, right there.
This one?
So he says that's what you get if you try and estimate, 150 degrees based, and he even talks about it being, I want to say in his 8-2 example. Unless I'm referencing this wrong. Yeah.
So I think what we're running into with the diagrams is, again, the problem with having both of this represents both the input and the output. Actually, let's flip these around. How hard is it to? Oh, not hard. I'm going to flip these. Okay. Will they be? Ha, sweet. Okay. So that worked. So is this any closer?
And did he show a picture and what it looks like? No, we're still in superposition.
Well, see, here's the thing. So it is in superposition.
It's before reading. That's where I got.
But in this part, this is only showing the 8 qubits that we have in the output register, or the 3 qubits that we have in the output register that give us a value of 8, right? or between 0 and 7. So in this case, we have 16 circles showing up because the input register is also part of this.
Yeah, but I noticed if you put your cursor right before the reads, right before the very end, that looks more like what he had in the book. And one thing that I thought was interesting is, okay, 150, and he has this diagram. Okay, if you only have 8 bits, 3 qubits worth of precision, 150, you have 135 or you have 180, and 150 somewhere there in the middle. And I thought, well, it's closer to 135. So I initially thought that's why your bit 11 is the largest. And I'm sorry, your output 11 is the largest and your output 12 is the second largest, because it's actually closer to 11. But there's still that noise across. And that's where I'm like, shoot, here once again, we can run 1,000 iterations and hopefully we'll get close. In my mind, I was thinking, this should have been clean. I should have had like a 65% chance to get output 11 and then the remaining percent to get output 12, because it's in between those two. And he's saying, no, there's a slight chance you're going to get output 8. And so that was another thing for me to say, yeah, this isn't precise, isn't it?
Yeah, as soon as you get off that exact number, it just kind of spreads everywhere. So
well, not to state the obvious here, but the title is phase estimation.
Estimation, yes.
Just saying, just someone had to.
Yeah, so if we do the same thing with, actually, let's do 3. So we have the same number of circles again.
Do you want to reverse the registers?
Yeah, I'm gonna flip them.
That was good, yeah.
Okay, we'll flip the registers, and then okay, why aren't you going? Okay, there we go. 2 rows. Go to 2 rows. This visualizer is a little janky, and I don't know if it's my browser or what. But here, if we're right before we're at that, is this that same? Yeah, like the same 8414. But I don't know. I haven't gotten any other values out of this. So it seems like the read, since it does fit into the resolution, it's exact and you can't get another value.
Well, it's because of the divisibility. Certain problems are not evenly divisible and other problems are.
Right. Oh, okay. And actually, I'm being confused by this diagram because, again, the input is part of this.
Yeah. Because
our input is unchanged. That's the whole trick. So our input is unchanged, but it shifts down, this many bits, which turns into our 180 degrees precisely.
Yeah.
Whereas in this one, well, it's not going to shift because it's not the same state, but it kind of gets spread out rather than just shifting cleanly by 4 places or whatever it was. So, okay, how close is that to the diagram? Pretty close.
Your bottom register is.
Yep. I think we got it.
Yeah. Although it's upside down.
Yeah.
Compared to this, it looks like. But again, since we have our original register, our input register as part of this, yeah, it'd be nice if we could just visualize, have circle notation for just the output register. Yeah, so this is the experiments that I did. And again, I'm kind of going on faith that this is going to be useful. When it came to, here's how the QPU works. Again, I kind of went with this. I like this, the intuition. And okay, well, here's the idea of, okay, again, we kind of have our circles that are rotating And based on that, our inverse QFT gives us the value out of that. And so it's interesting that it builds on the QFT stuff that we saw in the previous chapter. And again, as far as the rest of this I think probably explains how that loop works, based on the number of qubits. So in this case, there's kind of like an unspecified number of qubits. Is this one the input? The eigenstate would be the input,
Well,
right?
it's interesting what the text says up there. It says, we'll now see we can build up a circuit to achieve this kind of conditional rotation by combining the Kant U subroutine, providing conditional access to U, with the phase kickback trick, which I don't remember what that is. Do you guys remember?
Phase kickback.
Yeah.
Okay, I'm gonna see if that's in the index.
Yeah, because it also comes up later, and it was something that I was like, I need to look that up because I didn't remember.
It's on page 50.
Okay.
It actually is in the index.
So, because again, this is building on something we saw earlier that I don't remember how it works.
Okay, let's see if I can find that.
Okay, sorry, I don't mean to put you on the spot, but it's something.
Oh, no, that's fine.
Because it comes up in another chapter too, and I hadn't looked it up yet, and I was like,
indexing.
well, there's that link too, right there where it says chapter 3.
Yeah, it says okay.
Yeah.
It's chapter 3. Although I don't know how far into chapter 3 it is. There was a diagram and there was a heading that said phase.
When you get QPU instructions, C phase and CC.
Oh, okay, there we go. Yeah, yeah, it was related to the C phase. Okay, yeah.
Yeah, so one more.
Phase kickback. Okay. So let's see. Once we start thinking about altering the phase of one QPU register conditioned on the values of qubits in some other register, we can produce a surprising and useful effect known as phase kickback. One way to think of this circuit is that after placing register 1 in a superposition of all its 4 possible values, we've rotated the phase of register 2 conditional on the values taken by the qubits of register 1. However, looking at the results of individual states of both registers in circle notation, we see something interesting has also happened to the state of register 1. The phase rotations we try to apply to the second register, conditioned on qubits from the first, have also affected different values from the first register. Wow. Okay. So conditional. So we have a conditional 45 on register 1, which would be like this, and then a conditional on register 2, 90, and then this is if both are applied, right?
So I'm trying to understand this. The 45-degree rotation we performed in register 2 conditioned on the lowest weight qubit from register 1, but has also rotated every value in register 1 for which this lowest weight is activated, the 1 and 3.
So it rotated the 1 and the 3.
So it's,
and then the 90-degree rotation is on the highest weight qubit of register 1, has also kicked into all values of register 1 with the 2 and 3 values. So 1 and 3 got a 45, and then 2 and 3 got a 90.
Okay. And they were originally in the same state as 0. Yeah?
Yes.
Everything?
So 0. So relative phase would be
Yeah.
0.
Yeah.
Because if we had 2 qubits in 0 and had
Right.
them, they'd all be relative phase 0.
Right. Okay, so if we had to say that 45-degree register action in English. Examine the register, the qubits, the phases of the qubits in register 1, and if something, then rotate them 45 degrees. But what is the something?
Well, the conditional is qubit 0x1 a 0 or a 1?
Okay.
If it's a 0, don't rotate it. If it's a 1, rotate it.
Okay.
So this is a phase rotation conditional on what this is.
Okay.
But because of the way phase works, this phase kickback, it actually ends up impacting this one.
Yeah.
So in the states where the 0x1 bit is 1, we'll end up with a 45 degree rotation.
Okay.
So again, that would be 0, 1, which would be this, or 1, 1, which would be 3. So if the
I
lower
get
bit
it.
is
Okay.
1,
I got it.
Yeah.
I got it. It took me a minute. Does it make sense, Matt? Did you get it?
Yeah.
It's the binary binary representations.
Yeah, where I'm caught, and this is where I feel like I have a gap in my remembering of chapter 3. It says on the lower left there, one way to think of the circuit is after playing register 1 in superposition, we've rotated the phase of register 2 conditional on register 1. Now, what he goes on to say is it actually affects register 1 also.
Yeah.
Mhm.
And I think that's the kickback. But
Yes.
where I'm having trouble is register 2 never changed.
Well, again, we're talking relative phases. So if register 2 is a 1, right, has a value of 1, or 100% chance of being 1, right? There's no superposition on register 2. So since we're talking relative phase, it doesn't matter, because since the 0, it kind of doesn't have a phase because there's no chance of it being
I see.
Being the value. So even though register 2 is rotated, since we say it's a relative rotation, it ends up kind of being no rotation at all because it's relative to a 0 or nothing.
Because 0 never ever possibly be an option.
For register 2, correct? Yes.
There is no relation. So you might as well. He could have rotated the 1 there, but it doesn't mean it.
Correct. That's what I would. Does that sound right to you, Lynn?
Yep.
Okay.
Boy, that was good to review. Thank you.
Yeah, it is. Okay, so except I lost my page.
So how are you doing on presenting the content, Jeremy? Because we are at about an hour now.
Yeah, I don't have anything else.
Okay.
I think that's pretty much it.
Yeah. So
okay.
So
that was pretty much it. Okay.
Awesome. So thank you really a lot. So in terms of going forward, I am really working on chapters 12 and 13 because 13 is machine learning and there are no code examples, and I got a bunch of them. And 12 is Shor's algorithm, which is, if we're going to go forward with this in any of our learning, that's where it starts. Like Shor's algorithm is like hello world. So I want to do a really good job on that. So not to put you on the spot, Matt, but do you feel like maybe doing 9 or 10 coming up?
Sure, I can do one or the other. Jeremy, just if it's consistently us 3, and you just presented and you presented the week before, I kind of assumed I would go ahead and take the next one.
Yeah, so 9 is, because I reread the whole thing, and 9 is encoding data. 10 has to do with logic and applications, which I know you really liked that. 11 is graphics, which is to me one of the most fun chapters.
Yeah, that's interesting.
Yeah. So I will definitely do 12 and 13. 14 isn't. 14 has, here is the future and here's a bunch of algorithms we're not going to explain. So I think we should end at 13 because that's a really, really big chapter. And if Nuri joins again, maybe Nuri can take one of them, but I'm kind of hoping that you guys can do 9, 10, and 11, and I can focus on 12 and 13, if that's cool. So,
Yeah, I can do 9.
Great.
And if he's willing, he can grab the next one. If he's not available, then Jeremy, I can just flip flop until Mary's
Yeah,
available.
yeah.
Till we
Okay,
get-
great. I'm going to stop the recording here.